All right, welcome everyone. Today we're going to start looking at surface integrals, integrating a function over a three-dimensional surface. Okay, and that can include enclosed bodies or just an actual surface, right? Just kind of this sheet that we're running across. Okay, and integrating some function across that surface. All right, so let's start to share the doc cam, and we'll get going here. All right, so now we're going to deal with surface integrals, right? So before, earlier in our discussions, we had gone through, sorry, let me get my mouse cursor out of the way, there we are. We had gone through line integrals, right? Integrating a function over some path. And we had identified some kind of brief physical meaning what that could represent for us. The big part of it, though, is our calculation, allowing that function, right, to act on these little segments, these little bits of arc length over that path that we were integrating. So now with surface integrals, what we're going to kind of do is, again, starting off with some region, whatever that might be, right, in our domain space with our two parameters, u and v. It could be x and y, right? Then we're going to use a parametric function, right? This vector value function to kind of point us on different locations on the surface to create then some surface S, right? That these points UV are getting mapped to on that surface. Okay, and we had talked about that if we wanted to produce some little S sub ij, this little segment, right? Or I might call it here some little ds, let's say. Okay, some little segment of that surface area. We would begin by using some little dA in our parametric space. Okay, and what we had identified was that the integral over our surface ds we can compute by taking the integral, the double integral over that region D of this cross product R with the partial derivative with respect to U, R with partial derivative with respect to V, those two primers, we could do X and Y. That cross product of those two partial derivative vectors, dA. Okay, and we had worked on that somewhat in our previous lecture. And as we can define, if our function we're assuming is a function of x, y, z is a function of x and y, we might look at it in terms of, right, that 1 plus dz dx squared plus dz dy squared dA, right, where our surface is a function z of x, y. We can rewrite this z is a function of x and y. We can kind of rewrite, and that's what we did in that previous lecture, right? So now we want to integrate a function. Let me go f of x, y, z over the surface S. right? And so the way I kind of visualize it is that that function f of x, y, and z acts on the little segments Sij across the surface. Okay, so here, shift this up. We might have our surface. It can be a closed surface later, okay? But for these little segments, these little blocks of surface area, we're going to let some function f of x, y, z act on that little square. Okay, so what we're going to see is this integral over s of our function f of x, y, z ds. Our function acting on, working against each of those little segments, ds. Okay, and what we saw with our integration work yesterday, that we can actually rewrite that double integral as this double integral over this region D over which we're integrating, right, parameterizing. And now we have our function f of now that r of u v, how we're parameterizing that surface, the parametric surface, multiplied by that partial of r with respect to u crossed that partial with respect to d, a partial of r with respect to v, d a. Right, so taking a little ds component, which we built up in our previous lecture, and now acting upon it with this function. Right, so now we're starting to accumulate what those actions might be. And so later when we start to get to our vector fields flowing through a surface, okay, it's going to be kind of like measuring these particles passing through that surface, acting through that surface across that entire body, okay? But here's our kind of way of starting to compute, starting to manage those components, okay? And so then rewriting these again, which we're going to kind of commonly see, right? And so for our surfaces where x and y are the parameters, right? Z is equal to some function of x and y, or I think the book might use g of x, y, so we don't confuse that function that we're integrating with actual surface, okay? Then when we look at our integral over that surface S of this function of x, y, z, and again, that's why we want to kind of use a different letter, ds, this becomes this integral over that surface S f of x, y, and now if z is g of x, y, right, that parameterization, ds, and then we go into that double integral where that ds component we replace with that dz dx squared plus dz dy squared plus 1 dA. Okay, and, pardon me. And depending on how we parameterize, right, with some of the problems that we may be seeing on the exam one, if x is staying the same, but we're parameterizing the other components in terms of y and z, we have that cylinder, right, running around the x-axis. then maybe it's our equation for that surface is y squared plus z squared equals 1 or whatnot, or x is a function of y and z. We just swap these out, right? Then the function goes with the x component, g of yz, and we're going to have our dx dy, dx dz plus 1 dA. And we just have to kind of reorganize those components, right? Depending on how that surface is built up. Okay. And so the idea then we're going to have this function acting along that surface and integrating like so. And so what I want to bring up, and we can look at an example. If we have a fully enclosed solid, right, surface that we are integrating over. And our textbook uses this symbol, this notation, E. Then we may need to separate that surface into its separate parts to integrate, right? To integrate over, to integrate across. So for this example, right, what if we think about we want to integrate over a cylinder? Right? If we have this cylinder, that we want to integrate over, there's my close surface S, or E, pardon me, over which I want to integrate. Okay, and I'll do our kind of more formal notation for a moment, right? So I want to integrate over this surface, this function, and there's my little ds part of it, right? What we have to notice is that, well, depending on how we're going to organize, we have three different surfaces to manage. We have the top, we have right that body, and then we also have the base. In this problem, okay, what we have to notice is that E can be separated into three different surfaces, right, to create that full body. S1, that's the top portion. S2, the body of it. And S3, the bottom, the lower portion. So when we actually think about evaluating that surface integral, B, D, A, we actually have to separate over those three different parameterizations for those parts. Okay, and we need to parameterize each surface separately. So we're going to have an R sub 1, R sub 2, R sub 3. And some of these might be useful to do in terms of polar coordinates, R's and thetas, right? Or X and theta, whatever it might be, as we start to build up those expressions, right? We might parameterize in terms of X and Y. It all just depends on how we're kind of manipulating to create those surfaces. And that's where sometimes it becomes a lengthier problem when these enclosed bodies, because we have to separate out into those different pieces. And we start to look into the next section, the next discussion, we're hopefully going to find some ways of managing some of these surface integrals and rewriting them in terms of other calculations to simplify, just like we did with our line integral. We had Green's theorem. Instead of having to go through that boundary, we converted to a double integral, integrating over the area that it encloses. So what we're going to start to talk about with some of our other theorems is how we can convert this surface integral to possibly an integral of this volume. But again, that's getting ahead. For now, these surface integrals, taking those components and integrating across those different surfaces. All right. So then let's look at an example of this surface integral discussion, and we can work on this process. Okay. All right. So here we go. So for example, let's check out this problem. Let's look at number 8. This is on page 1173 from our text, that calculus 8th edition from Stewart. And we're going to evaluate this surface integral, just double integral over s, x squared plus y squared. So there's our function, ds. And s is the surface with vector equation r of uv is equal to 2uv u squared minus v squared, u squared plus v squared, where u squared plus v squared less than or equal to 1. Okay, so this idea, I guess I need to expand this. There we go. This portion is like our region D, the domain. And with that u squared plus v squared less than 1, this is a disk, a circle with radius 1. So what we're doing, we're taking that region, taking these different points, u, v in that space, and we're going to go through our equation, r of uv, to produce this surface. And again, we can go through our graphing utilities, but I'm just going to kind of make this up. We should have some rounded edges. There's our s based on that function. And as we go through, we see like this is our x component, there's our y component, there's our z component to give us the location on that surface. Okay. And again, we could do a better job of graphing it, but for now I'm just going to kind of focus on the calculations. But we could go through this in a graphing utility to start to plug in. Okay. All right. So with that said, let's start to go through this calculation, right? And so we talked about before that when we're integrating some function of r of uv Okay. D S. This was integral over D. F of R of UV times that magnitude R sub U cross R sub V dA. Okay. So let's start to put this space together, right? So first up, R of UV, 2UV, U squared minus V squared, U squared plus V squared. So my R sub U, the derivative with respect to U, 2V, 2U, 2U, right? The V squared minus V squared is 0. In this case, multiplying V is a constant. R sub V, 2U, negative 2V, positive 2V. So doing my cross product of those, I, J, K across the top, row, R sub U, 2V, 2U, 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 negative 2V, 2V. Computing here, I, column, row, 4UV minus a negative, so that turns into plus 4UV, minus, now for the J, 2V squared, minus, 4V squared, 4U squared, 2V times 2V, 4V, minus 2U times 2U, 4U squared, and then plus for the K component, negative 4V squared minus 4U squared, K. Okay. So working on that. Let's see this magnitude. Okay. And so the magnitude RU cross RV square root of the sum of each of these components squared. Well, that's going to be 8UV squared, but I'll do that in a second. Show that negative again, sorry. Boom. Then this is negative 4b squared minus 4u squared squared. Okay. So going through that work here. Let me simplify here. That's going to be at 8uv squared plus negative 4b squared plus 4u squared squared plus a negative 4u squared or 4b squared minus 4u squared squared. I know it's a little bit choppy there. My apologies. But let's see here. Now, expanding that out, 4 times 4, we get 16. B squared, negative 4, B squared times a positive 4, U squared 16, negative 16, B squared, U squared, then 4 there, another 6, so minus 32, right? Double that. U squared, B squared. plus 16 u to the, that should be u to the b to the fourth, u to the fourth. And then similar over here, another 16 b to the fourth. These are both negative, so it's going to be negative. Negative will be positive, so plus 32 u squared b squared plus another 16 u squared, or u to the fourth. So what does that turn into? Combine our like terms here. 16 plus 16, sorry, 32 u to the fourth power. It's a little messy here. These go away, but we still have a positive 64 u squared b squared. And then another 32 b to the fourth. Factoring out at 32. We're going to have the u to the fourth plus 2u squared b squared plus b to the fourth, which 32 u squared plus b squared squared. So at the end, simplifying that, we get u squared plus b squared. The square root of 32, simplifying here, 16 times 2, right? So 4 over 2. We can carry that around. So there's that cross product magnitude. Messy, I know. But let's start to work on this, okay? So with that work, we're starting to see, hopefully, this integral then, for our span. Let's start to look at this again. If this is a region D, over which we're integrating, both that circle, that disk, it probably supports that we can use this polar form, polar coordinates. U can be like our x, our cosine theta. V can be like our y, our sine theta. In this case, r is equal to 1. So u is going to be the cosine of theta. V is going to be the sine of theta. Okay. So when we start to look at that cross product magnitude, let me sneak that forward to up front, but we had that u squared plus v squared. That's going to turn into cosine squared theta, sine squared theta, which of course is 1, Pythagorean identity. So in this case, that magnitude is just that constant 4 root 2. Okay. Or actually, I can keep the r in my apologies here for these positions. R. So it's going to be r squared, 1 r squared there, better. Okay. Because we're going to range from there. Because now with that span, now for that region D, that dA component of it is r dr d theta. Okay. And r goes between 0 and 1. There we go. Theta, since we're taking that full disk, between 0 and 2 pi. a lot of discussion back and forth here. So then our integral, going back to the earlier problem, the integral over s over x squared plus y squared ds, right, where our r of uv to uv u squared minus v squared plus v squared, right? It becomes this integral over the region D, Rx to uv squared plus our y, u squared minus v squared squared. So there's my function in terms of u and v. We'll do the cross product here for a second, dA. Okay. So then as I start to go through, u was r cosine theta, v r sine theta. So we have that quantity squared plus in here u squared r cosine theta squared minus r sine theta squared, that quantity squared. And then what we had done here, remember that was 4 root 2 r squared. And then the dA component, r dr d theta. And so since I have my units here, r 0 to 1, theta 0 to pi, and a lot of algebra to clean up. Simplify inside here, I'm going to bring these components up front. 4 root 2 r cubed, r squared with the r. And now let's check out what's going on here. We're squaring this piece. So first up, it's going to be 2r squared cosine theta sine theta. Then we're going to square that. So it's going to be 4r to the fourth cosine squared theta sine squared theta. Plus, and now r squared cosine squared theta minus r squared sine squared theta. And we could incorporate some of those double angle identities, half angle identities, right, to simplify. But if I just square that component, we're going to get here with r to the fourth cosine to the fourth theta minus 2r to the fourth cosine squared theta sine squared theta plus r to the fourth sine to the fourth theta. And that's still dr d theta. Looking at the terms, right, combining where we can, simplifying, so on, it becomes, right, kind of messy, I know, but this tedious task, trying to simplify down where we can. R to the fourth cosine to the fourth theta plus 2r to the fourth cosine squared theta sine squared theta plus r to the fourth sine to the fourth theta dr d theta. And here we might see some of those simplifying techniques, right? We can factor out r to the fourth, and then this becomes a cosine squared theta plus sine squared theta squared dr d theta. Which this is just a 1. So in the end, this becomes this integral from 0 to pi, 0 to 1. That's just a 1 squared 1 4 root 2 r to the 7th power dr d theta. A lot of tedious algebra there. The big part of it was, of course, setting up and then seeing how we rewrite. All right, but going through that process, what I'm thinking about later is hopefully this interval can be simplified down in some way instead of having to really manipulate that surface, right? But again, if we do, parameterizing is going to be a big deal. Simplifying down. And then we can evaluate here this not too terrible of an integral, just watching out for those terms. Okay. All right. And so imagine if we had a closed surface, instead of just a simple S of this surface, we have it enclosed and having to do that for like 3 different parameterizations, right? Think about that cylinder we're enclosing. Having to go through that, simplifying, and again, if we parameterize that R may be different for each of those surfaces. So then we might not get that same expression here. We have to kind of focus on, okay, what's the X look like? What's the Y look like? What's the Z look like? In order to parameterize and then fill in our function, that X squared plus Y squared accordion. Okay. All right. And so then getting into this last bit of discussion with the surface interval, what if we had, right, that vector field? Okay. And so then when we start to look at these surfaces, right? So surface integrals with vector fields. So what I can imagine is that if we have, again, my generic surface here in our coordinate system, and now through these little ds segments, we're going to have this vector field kind of like traversing, working through that surface. And again, depending on what that vector field represents for us, it might have different, like the flow of particles through, charged particles through this magnetic field, whatever it might be, the accumulation of charge on the surface, the flow of our water through some space in a river, through a pipe, that kind of idea, okay? So we have it working through the space. And so when we look at this with our vector field, okay, for each one, we have our kind of X, Y, Z components. I'm not trying to get too intricate here. All right, where this is some function P, Q, R of X, Y, Z, okay? Like so. When we go through, we need an orientation for that surface. We know, okay, which direction is that surface kind of oriented facing, if you will, that we're identifying. So that way when we see the vector field pushing through that surface, we're going to see how that surface kind of and vector field mesh together, how they're going to working with the components, right? Thinking about how we had done our force, right? Is that force to move the particle go in the same direction, or is it opposite direction? Okay, the negative work, these kind of ideas start to come into play. And so in this case, for a positive oriented surface, okay, this orientation, that positively oriented surface is that we're going to see, we want that surface to be pointing kind of outwards, upwards. Okay. Our normal vectors point outward from the surface. Right, especially with those kind of enclosed cylinders, we kind of have this idea we don't want to go inside that surface. If we think about like concavity with our surfaces here, concave down, concave up, right? That kind of idea. And so in this case, for the surface, we're going to want to identify this kind of normal vector, and we can do a unit normal as well. In order to evaluate. Okay. Let's put that back. And hat. We'll do a unit normal. Okay. For that direction. And so what happens with our integration, integrating over that surface S with our vector field with these bits of our surface, we're going to integrate over our surface, and to get this surface as a vector, right, orienting that surface at R of UV, we know with our unit normal and our typical kind of ds, right? And so for this ds component, that's R magnitude RU cross RV dA. And for that unit normal, we can find that direction, right? If these are like our tangent vectors in the UV direction, and I want a normal, so I want the cross product to be perpendicular orthogonal to those. You want it to be a unit vector, so we divide by that magnitude. And then our function for our vector field becomes f of r uv, depending where we are with x, y, z. We can plug in our u and v. So then this integral, when we're multiplying those components together, this becomes this integral over the region D of our f r of uv, the parameterization of parametric surface, multiplying by ru cross rv over the magnitude, ru cross rv, then our ds component, that magnitude ru cross rv dA. I notice here, these are multiplying, those are scalars, those can cancel. So we saw this dot product to give us a scalar result of this vector field R of UV dotted with that cross product RU cross RV dA. Again, I know it's a long process parameterizing getting through, but as we start to do the dot product with this cross product, okay, in turn, this becomes again building from our surface integrals, our surface integration, the surface area we did in the previous lecture. This, all right, this is kind of like our PQR. This cross product we had worked on yesterday, negative dz dx, negative dz dz dy, and then this is just 1. When I take that dot product, negative p dz dx minus q dz dy plus r dA. Okay, and again, that one's going to take some time and thought, but we'll see how we can use this work integrating over some of these surfaces, closed surfaces, right, closed bounded volumes with some theorems to help simplify having to parameterize so much. Okay, all right, leave it at that. I know it's a lot to take in anyways. Definitely look at some of the examples in the text to support some more examples of these surface intervals worked out.